Okay, so in this video, we're going to integrate a trigonometric integral using Cauchy's residue theorem. Okay, and so in the previous video, I discussed how we convert from an integral with respect to theta to an integral with respect to z. That's a contour integral. Okay, but what's different in this problem is we have this cosine 2 theta that's in the numerator. Okay, and so I'll show you how to deal with that. Of course, cosine 2 theta has an identity in terms of cosine theta and sine theta. Okay, but there's a better way to go about this problem. So notice that, or if you recall first, that we let z equal e to the I theta. Okay, and if we actually square z, we get e to the I 2 theta, and if we use Euler's formula, this is cosine 2 theta plus I sine of 2 theta, right? And also, z to the minus 2 equals e to the minus I 2 theta. In using Euler's formula, this is cosine 2 theta, using the fact that cosine is an even function, minus I sine 2 theta, using the fact that sine is an odd function. Okay, and then if I add sine squared and sine to the minus 2, I can come up with a formula for cosine 2 theta. So from this, we find that cosine 2 theta is equal to 1/2 z squared plus 1 over z squared. So this is what we'll substitute in for cosine 2 theta. Okay. So our trigonometric integral becomes integral over c, where c is the unit circle, of 1/2 z squared plus 1 over z squared divided by 5 minus 4 times 1/2, which is 2, and then times z plus 1 over c. That's substituting in for cosine theta. And then d theta, if you recall, is dz over iz, right? So of course there's some algebra we need to do to simplify this expression to get it into a nicer form. I'll let you do that as an exercise. I'll basically write down what we get, which is we get I times z to the 4th plus 1 in the numerator, and in the denominator we get 2z squared, z minus 2, and 2z minus 1 in the denominator. Okay, so now that this has been simplified, we need to use Cauchy's residue theorem. Okay, so we need to basically locate the singularities of this integrand, and I'm going to label this as our f of z. Okay, and then we have to determine which of those singularities is actually inside the unit circle. So it's pretty easy to see that. We have 0 is a pole of order 2, and 1/2 is a pole of order 1. And both of those are inside the unit circle, right? So we can compute this integral by computing residues. So actually, we can write out the details. We can say that using Cauchy's residue theorem, that this integral is 2 pi I times the residue of f at 0 plus the residue of f at 1/2. Okay, so now we'll compute both of these things, all right? And so remember, 0 is a pole of order 2, 1/2 is a pole of order 1. All right, so to compute first the residue of f at 0. Okay, using theorem 1, this is equal to the limit as z approaches 0 of, it's a first derivative of z squared times f of z. This is just using theorem 1 in chapter 6. Okay, And so this equals limit as z goes to 0 of a first derivative of I over 2 times the fraction z to the fourth plus 1 over 2z squared minus 5z plus 2. Okay. So now we have to differentiate this fraction, this rational function, using quotient rule, and it's not too bad. So we have a limit as z goes to 0 of so let's see here. In the numerator, we have 4z cubed. It's a derivative of the numerator. Times the denominator, 2z squared minus 5z plus 2, and then minus our numerator times the derivative of the denominator, which is 4z minus 5. And then we take and we square the denominator. Okay, and so there's, so notice I did not square this 2 because I factored out a 2 that was in the numerator. Okay. All right, so this is the limit that we want to take as z goes to 0. All right, so that's kind of nice in that all of these z's get wiped away when z is 0. So we plug in z equals 0. We get that this is I times, so this term in the numerator is 0. We end up getting a minus 1 times a minus 5, or 5. And then in the denominator, so this is going to be 2 squared times 2, which is 8. So we have this as a result for the residue of f at 0. And so for the residue of f at 1/2, so this is a simple pole, so we have the limit as z approaches 1/2 of so it's z minus, so we take the limit as z approaches 1/2 of z minus 1/2 times f of z. And after canceling out so we're going to have an I, z to the fourth plus 1 in the numerator, and then in the denominator, we have 4z squared z minus 2. Okay. And just plug in 1/2 in for z. And I have that this is equal to minus 17I over 24. Okay, so we've computed the 2 residues, and from the board that we had written down previously, our integral was equal to 2 pi I times the sum of these 2 residues. So we have a 5I over 8 minus 17I over 24. And if we simplify this expression, the result is pi over 6. So this integral here is equal to